Hello, everyone. So we have 2025 MATHCOUNTS chapter problem. So this was last questions on the spin test. So we have div 26. How many order triples of the odd integers, odd positive integers, A, B, C, satisfy this equation, and A is smaller than B, that's smaller than C. Like there are a couple of ways to approach this one. Like since 49 is not like too big number, especially when you consider the odd numbers, we actually can go with the kind of cases. I'll try that first for those like who doesn't know the sudden bars. So which is why if I go with like 1 for A, maybe I should use this way. So the A of B C will be 49, right? So the first thing is like if I choose this is 1 and that has to be 3, that's 4. That's even number. When you add the third odd numbers, you'll get odd, which is reasonable. And that will give us 45, right? And then after that, you can list this more, like keeping 1 as it is. And you can go with like 5, and then that will be 2 lesser. So you'll get 43. You don't want to list everything. We just want to see what's going on. And then when you add these two, you get like 48. So the half is 44. So which means this might be 43. And then this might be 45. Okay, so when you add them, so you get like 48 in total. So we have the triples, 1, 3, 45, 1, 5, 43, and all the way 1, 44, 43. So we just want to know how many of these. Like if you start with this 3, and then you are increasing by 2 every time, so all the way to the 43. The short way we were doing, like for the number of terms, was like the last number minus the first number, divide by the change, which is 2 in this case, and then add 1. So this was the number of terms. So you will get 20 over 2, which is, let me double check this. Actually, this was 23, not 40. So let me put it back. Okay, so 23, 25. So now you get 23 minus 3 over 2 plus 1, which is going to be 11. So the first thing is 11. So we have 11 option, 11 like triples. If A is 1, and then B and C can be swapped with different pairs. So now the second case, like if I go with, like I am done with 1. So if I go with 3 as the smallest one, and next one will be 5, which is 8 add up to. So the last one should be 41 to get 49. So I can play with this. I'm not going to write everything in the middle. So the last one should be like, the sum is 46, the half is 23. So that means this has to be 21 and 25. So I will do the same thing with my half. So 21 minus 5 is 16, divided by 2 is 8, 8 plus 1 is 9. So we have 9 more pairs, triples from here. Okay, so now we got that. And the next one should be like a 5, 7, and then that's 12. You subtract, you got 37. So if you add those, that's 44. So half is like 40, like, I mean, 44, that's 22, but 22 doesn't work. So you will go with 21 and 23. So that 21 minus 7 is 14 divided by 2, 7 plus 1 is 8. So which is why it's going to be 8. So it was decreasing by 2, but now 1, so which means there's no certain pattern. We want to check everything to feel safe. Okay. And the next one will be like 7, 9, that's 16. If you subtract, so you will get 33 left over. So that's add up to like 42. Half is 21, but 21 doesn't work, so you should have smaller than the other one. So you will get 23. So between 9 and 19, like 19 minus 9 is 10, divided by 2 is 5, plus 1 is 6. So we have 6 more. And the next one should be 9, 11, that's 20. So you will get 29 left. And that's add up to like 40. The half is 20, so it has to be 19 and 21. So you can go ahead and count them like 11, like 13 all the way to 19, but I'll use the number of term stuff. So 19 minus 11 is 8, divided by 2 is 4, plus 1 is 5. So we get 5 more. And if I continue in this, I will have a few more. So that should be 11 or 13. That's 24. So you will get 25 left over. So that is add up to 38. So 19 is the halfway. So you should get 17 and 21, I believe. So 13, 15, and 17, which looks like just 3 more triples from here. And let's see if we have more. So if I go with like 13, so you got 15, that's 28. So from 28 to 49, so you will get 21. So that looks good. And then I can go with 17, and that will decrease by 2, which is 19. So that's just 2 more. And then we cannot have anything more like than this. So if you add those, that's 20, and then 8 and 2 is 10. That's another 10, that's 30. So if you add this 14, which is 44. So like this is not too much work, to be honest, especially if you know what you're doing. So this is, I guess, reasonable for number 26. But this is one thing we can do. The second thing is, when you see this, maybe we can just play with this a bit, try to do it a bit differently. So like I can just replace this number as 2 times a prime minus 1, because we are told these are odd numbers, and a prime is just going to be an integer. And then b, I will write as 2 times b prime minus 1. And then same thing with the 2c prime minus 1, that is right up to 49. So the reason why I'm doing this, because when we use the starting bars, it's good to have the integers, that is everything like working. So if you add 3 to both sides, that's 52, and then divide by 2, you get 26. So you got a prime, b prime, and c prime is like 26. What is that telling us? So like a prime, b prime, and c prime are positive integers. So any integer, not just odd anymore. So, and the number of solution to this is going to be, we have like 26 stars, which means we will have 25 basically gaps in between. So, and then of those gaps, we need to make 3 groups. So we just need 2 bars. So that will be 25. Choose 2 ways to kind of give the numbers like a prime, b prime, c prime, or different integers, positive integers, okay? At least one. So that will be like 25 times 24 over 2. And then that will be 3 times 4. That's going to be 300. Okay, so this is 300. It's going to tell us every possible triples, positive integers. Okay, but although some of them are equal, maybe, and then maybe some like all three might be equal, or like some like two of them are equal. But when you look at these three, you are saying all three are equal. That's 26, which is not possible. But when you think in general, so all three can't be equal, but A and B might be equal. Like maybe if A prime and B prime equal, then we are going to get something like this: 2A prime plus C prime is equal to 26. So if this is 1, that's going to be 22. If this is 2, that's 4. That will be like 20. This was actually 24, and then this is 22. And then if you keep doing this, like, right, so the last one for C has to be even numbers. If this is 2, that's 24, so that should be 12, which means there are 12 numbers that actually works. If A and B prime are equal to each other, so then you have 12, I guess, triples, but it could be A and C are equal, or B and C are equal, so which means there are 3 different pairs that might be equal, so which will tell us 3 times 12. 36 triples actually should be subtracted from 300. So if you take the 36, and now this is going to be the number of triples that all like numbers are different. So one could be 1, the other one is 2, and one something else, all of these. And you know, when you have 3 numbers, there's only one way to order from smallest to numbers. And then there are 6 different ways to arrange those. So which is why this is going to be divided by 6 to fix our counting. So you got 264 over 6, I guess. So 26 divided by 6, that's 4 times. That's going to be 24. And then you got 2 left over, 24 again. 6 goes 4 times, and that is also 44. So like we did this 2 ways. And then if you didn't like this, as soon as you make this A prime, B prime, C prime is 26, you could use the first approach with that equation without using star and bars. But I kind of remind the star and bars because sometimes if the numbers are a bit like higher than these numbers, then star and bars are going to be, I guess, the best way to go with. Anyway, so that was number 26. Okay, so let's continue with 27. So we have 2 to the n be largest power of 2 that divides the expression given, and we want to find the value of n. Okay, this is slightly challenging, I guess, especially to see. So what I say, like we have 4 terms, we multiply, and then we multiply the next 4 terms and the next 4 terms and continue this pattern. So like we want to kind of make this a compact way. So we usually use like the sigma notation, which can be used as well. But let's try to see if we can do it a little bit differently. So what I will say, like, since we have 4 terms every time, that's a good reminder for us to remember like 4 factorial. So and then maybe write everything into 4 factorial times what's left over. So for example, the first one, like 1, 2, like 3, and 4, but there's nothing else. So I'm going to just say nothing, which is 1. And plus the second one, I have 2, 3, 4, which is already 4 factorial if you include 1 in front. So you will get 1, 2, 3, 4. And then the 5 is the last one left over. So let's remember these guys are 4 factorials. And then the next one is going to be like 3, 4, but I need 2 in front as well. So 1, 2, 3, 4. So like we take this guy, 3 and 4, and then 2, we take one of 2's right here. So that will be 15 left over. Okay, and then if you keep doing this, we can just write everything because as 4 factorial times something else, because we have 4 consecutive terms, that's 4 factorial can be written. And the last one is like we can write this 4 factorial times something, which is easier to do so as well. But instead of doing right now, let's try to see whatever we have right here is going to be useful so far. So like we can see like we are choosing 4 numbers, right, every time. And then this is like 5, and then this is 1, and this is 15. So like just think about this. Like we have 1, 5, and 15. Can we write those like number 1, 5, and 15? Something choose 4. And that might be maybe the trick. So like this number can be written like 4 choose 4. So let me write that way. And then this number can be written like as like this is like 5, which is 5 is like something choose 4 should be 5. Something choose 1 is going to be 5 as well, which means 5. So this is actually 5 choose 4. And then if this is 6 choose 4, then we are good. So then this is actually 6 choose 4 because that's 6 choose 2. And if you are not convinced, then you can just actually list the next one, like, and see if that's really the case, like 7 choose 4. And the last one based on this pattern should be so like the pattern, like this is we are starting with the 1, and then this is 4 choose 4, and then we start with the 2, and then this is 5, which is like 5 is like 3 more than the first number that we start in the product. So this is 25, 3 more will be 28. So we should get like 28 choose 4 as the last thing, and then we just have 4 factorial. But let's see if this really give us these guys. If that's the case, then we are safe to continue. So like 4 factorial is 4, like 3, 2, 1, and then 28 factorial, like 28 choose 4 is like 28, 27, 26, 25. Is divided by 4 factorial, which is actually good because that's going to cancel, which means this actually works for any of these. So now we can use this for our advantages because we have 4 factorial in every like sum. So that will be our product. So 4 factorial times 4 choose 4, and then you have 5 choose 4, and then we have 6 choose 4, and then it will continue all the way to the 28 choose 4. And then this is what we want to look at. And I'm not sure if you've seen such a thing. This is actually our hockey stick identity. Like when you see the bottom numbers are the same and then the top numbers are increasing by 1. So the result of this will be just 4 factorial times. So 4, 5 all the way to the 28. So you will increase the last one by 1, which is going to be 29. And then you're going to increase this by as well. So that will be choose 5. And the entire sum of these products is equal to 4 factorial times 29 choose 5, which is a really interesting relation with the Pascal's triangle. So if you didn't know the artistic identity, so this might be a good time to review as well. Anyway, so that should be 4 factorial. And then you got 29, 28, 27, 26. We need like 5 of them. 25 over 5 factorial. So we'll cancel these. I can cancel these 5 as well. So now we have no denominator, which is good. So we just need to know how many 2's are available. So 29 has nothing. 28 has 2 2's, and 27 no. 26 has 1 more 2, and then there's nothing else. So which means we have 3 2's in this product available. So that is going to be our answer. So like this was like slightly interesting to see, I guess. But if there are some other ways that you actually end up getting, so let me know as well. I'd like to see more approaches. So that was 27. Okay, so here's the number 28. So this is actually a cool problem. I kind of like this one. Even though like the question looks like requiring some, I don't know, calculus. So you actually can do this without using calculus at all. So what I would say, like if you have nothing like else, like you can square this and add one and kind of try to see, this is really close to 75 anyway, because adding one to a big number doesn't really make too much difference. So which means after you got the 75 point something, you can kind of get some decimals and maybe go from there. But that might be really hard because you will see the answer will not be that kind of close to 75. Anyway, so I mean, in terms of the digit after decimal point. So instead of doing that, maybe we can try something else, right? So what I will try is basically, 75 square is going to be like 56, 25. So which is something we can just square, and that's one of our perfect squares. And this is going to be one more than that, which is like 26, right? But what I will try to do, like, we have the square and root, so maybe we should use somehow to remove this guy. So I'll try is 56, 26, which is inside under square root. That's what we are looking for. If I actually square this and subtract 75 square, and then, this is going to be just like the number inside. And that's really close to like, this is actually what? This is going to be like 56, 26 when you remove square and square root, and this is going to be 56, 25. So this is going to be 1. Why this is going to be useful? Because now I have difference of square. So this can be written like 56 minus 26. I mean, 56, 26 on the radical minus 75 times 56, 26 and plus 75, which is equal to 1. Okay, so like, remember, this is what we are interested, right? So that's the value. And, since this is really, really close to like 56, 25, and now when you take the square root of 56, 25, this is going to be just 75, which means this is approximately 75 plus 75, which is 150, which is really close to that, right? If you divide both sides by 150, so you got like square root of 56, 26 minus 75 is roughly 1 over 150. Okay, so if you are not convinced with that, you may probably take a look at some derivative approaches, but for now, we are not interested. So now we can add 75 to both sides, so you will get 56, 26 is equal to 75 plus like 1 over 150. So the rest is just dividing 1 by 150, which is, I guess, not challenging either. So like what I can do is to make that slightly better, 25 times 6, so that should be 1 over 25 times 6, which is like 1 over 25 is going to be 0.04 over 6, and then you can just divide that by 6. So if you do so, I'm not going to do it right here, but you can just divide 1 by 150 or this way. So either one is okay. So like if you do this, we are going to get our approximation. I think that was 0. Let me check my work. So that was 0.006, right? Okay, I think that was the case. So 0.006. So, and then 6 repeating. So we should have our like repeating that part. So the first integer that does look like that is non-zero after this decimal is our 6. So that was our answer. So like the thing is, as soon as we discovered this is kind of this approach does kind of give us the answer. And if you are not satisfied, you can just kind of plug this into the calculator and see if that's really accurate, which is. But the thing is, as a kind of side note, like we didn't really show why this is actually working, but there is a square root approximation kind of formula or expression in general that we can use. So if you've never seen, it's good to review a bit as well. So when you try to take the square root of this, okay, b is a smaller number, a is like whatever number you're trying to add. So this is equal to the square root of a plus, okay, b over 2 times root a. And if that looks too challenging, which you probably don't have any idea about the derivative, because this is exactly what we do with the derivative of the radicals and stuff. So if you apply our problem, so that should be like 75 squared plus 1. And that should be like approximately, I'll say approximately, is equal to like the square root of 75 squared, which is 75. And then b is 1, so which is 1 over 2 times square root of this number, which was 75. As you see, this is exactly what we had as like 1/50, so that should be giving us the same thing. So again, this is good to review. So it's just coming from Taylor series to prove as well, and just using derivative. I hope that was clear. So I'll continue other two later on.